I'm from Toronto, and in Toronto, they fell in love with concrete and cement, and particularly in the 50s and 60s and 70s. So they built all of these linear culverts throughout the city, and what all that did is greatly exacerbate the flood risk because you're concentrating all of these flows into very linear channels. And of course, some of this was done because they wanted to maximize the amount of land that people could build homes on and things like that. And what are they doing now? What are they kind of woke up and realized? That's a really bad idea.
Land prices are very expensive in developing cities. There's a tendency to say, let's develop everything, let's concretize everything, and we'll somehow just build bigger drains in a few places and that's going to solve it. It's not going to solve it because you can never build a drain large enough. You have to make the whole landscape absorb and not focus on individual points where you can actually somehow mitigate everything. Welcome to the Water Data Podcast, where we talk about the science, the stories, and the systems that shape our water future. I'm your host, Veena Srinivasan. Every couple of weeks, we'll chat about how better data and evidence can result in better decision making and ultimately better outcomes for people and the planet. So if you're a student, a researcher, an innovator, a practitioner, or just curious about how we can better manage this precious resource, you've come to the right place. Let's get started. Welcome to the Water Data Podcast. It's a pleasure today and an honor to be speaking to Professor Richard Taylor from University College London. Richard is a specialist in groundwater and particularly groundwater in the context of climate change. And he's worked extensively in both East and West Africa. And it's really been a pleasure to work with him and discuss some of our work in India as well. Welcome to the podcast, Richard.
Thank you very much. It's a pleasure to be here.
Richard, in the Water Data Podcast, our entry point is around looking at data and understanding water resources through the lens of data, right? And of course, you've been, at this for many decades now. And I wanted to first start for listeners of this podcast to just think about why groundwater at all. Why should we care about groundwater? And just give them an introduction to that, and then talk about groundwater, particularly why its importance is increasing in the context of climate change.
I suppose the first argument or point I would make around what's distinctive about ground, it's the largest distributed store of fresh water on the planet. And so for communities around the world, whether they're suffering from drought or just the regular seasonal changes in their climate, it is the perennial store of fresh water, one that they can access throughout the year. Generally speaking, it is safer to access in terms of the quality of that water. Of course, there can be problems, arsenic and others that can be natural contamination. But the improved quality and availability and distribution of groundwater is absolutely fundamental to enabling people to have access to drinking water, perhaps access to water for more productive purposes, including irrigation. So, groundwater to me is absolutely fundamental. And in a warming world where we're moving towards more variability in rainfall itself, longer drought, more frequent droughts, it becomes the climate resilient source of fresh water for many people around the globe.
Let's kind of dive a little bit more into, firstly, what climate change is going to do and climate variability. I think one is to realize that climate has always been variable. But then, of course, it's getting more variable with increasing extreme events. So why does groundwater become more and more important in the context of that? And so a little bit about how groundwater acts as a buffer. And are we talking about the difference between shallow groundwater often and deeper groundwater, and how do each of those get impacted?
I suppose one maybe important fact to bring in is climate change brings tremendous uncertainty. And so we don't know, it's very, very challenging to understand where and when rain will fall or snow will fall. And the modelers hopelessly don't get this right. Although, to be fair to the modeling community, they're very good at predicting the degree of warming that's taking place. And air being a much easier parameter air temperature is much easier parameter to assess. But here's the interesting thing about air temperature. With global warming, it's actually rooted really in physical meteorology, is that it will take more evaporation will have to take place before you reach a kind of air, the air is saturated, because warmer air holds more moisture. And so from a very basic point, it takes more evaporation or evapotranspiration to take place before you reach saturation of the air itself, so that rain will fall or snow will fall. And what that means is, universally, globally speaking, and we have observed this is not relying on modeled evidence. Around the world, we're seeing that and then what we call an intensification of rainfall. So generally speaking, we would say fewer but heavier rainfalls. And this is leading to more frequent and intense droughts and more frequent and prolonged droughts. So as I was just explaining around the role that groundwater plays as this buffer, groundwater's importance really in a warming world becomes heightened, because people will find themselves in times of need, because when water is around will be less frequent or for shorter periods of time. And when they're in need of water, when there is the absence of water, these sort of periods will be enhanced. And so the role of having access to groundwater during those periods will become more important. So that's a kind of fundamental point. I've forgotten now the second part of your question.
No, I think that covers it really well. I think I'm just going to unpack a few things that you said, which is, of course, that when it's drier, it takes longer for the air to get saturated, which is what leads to the prolonged drought,
Yes.
right? Because
Yes.
it doesn't rain as quickly. Firstly, the oceans are evaporating also a lot more, so the total amount of moisture that's going to get delivered into the atmosphere also increases because of warming. But then when it precipitates a lot more, which is why you have these prolonged droughts and prolonged floods, right?
Yes, and that you brought up an interesting point. So a big debate amongst the climate change community is there a tendency towards wet places getting wetter and dry places getting drier? And there's been much debate about this. But it is the case that where areas are where you have this increase in the intensification and volume of rainfall, one of the curious things we're seeing is actually, I used to, for instance, in my teaching, say in a warming world, when you have ice sheets melting into the oceans, and you have snow and ice from glaciers, mountain glaciers, all of this being brought into the hydrological system, that there'll be more water circulating around the planet. And that indeed is true. But I often made the fatal flaw of thinking that the land and the oceans would receive this equally. And so you think, more water circulating around the planet means more water resources for people.
Which is great for dry places,
But actually, what we're seeing is, because the planet is more than 2/3 ocean rather than landmass, we're actually seeing that the net contribution to land is decreasing, and that the oceans preferentially are receiving more, and that's actually consistent with this wet gets wetter, dry gets drier, because actually
the oceans are wetter.
That's right. The wettest places on the planet are actually over the tropical oceans. So areas, for instance, in the Western Pacific, these often receive the greatest amount of rainfall. So I know we often talk about areas in northern India as being the wettest places on the planet, okay? But actually, the wettest places in the planet often in place, and maybe over the tropical oceans, so particularly the Western Pacific. Just important to recognize just how, also with this shift from fewer but more intensive rainfalls. One of the things that in the research that I've been doing, and this is borne out from observations, not from models, has been, we've actually been seeing that this has had in many environments, and not all, but particularly in the tropics, we've been seeing that this actually has led to increases in recharge. And it sort of stands to reason. If you think, for instance, around the tropics, where evaporation rates are generally consistent around the year. I mean, you don't have vast changes in temperature like we do in Britain or in Canada, where I'm originally from. What happens is that creates, if you want to call it, a threshold, meaning the light rainfalls of a few millimeters, The soil really doesn't think much about those, and groundwater doesn't even know that those existed. But when you have those very intense rainfalls, these can overcome what we might call soil moisture deficits and allow for the percolation and infiltration of water into the aquifers themselves.
Because the first rains are actually make the soil wetter, and it's only when the soil gets fully saturated does recharge actually happen, right? But not exactly also.
Not exactly. And I think you probably wanted to bring that up. This idea, what we're seeing often in some environments is, and this maybe gets back to data. For a long time, we didn't have very many measurements of how groundwater levels changed over time. And we particularly didn't have high frequency, or meaning very regular measurements, say hourly or daily. It's only with advances in technology and more and improvements and the expansion in the database of groundwater levels being monitored that we've begun to better understand the relationship between rainfall, precipitation, and its impact on groundwater levels. And I think many hydrologists were operating on the assumption that it takes certainly years, if not decades sometimes, for water to percolate from the surface all the way down to a water table. But actually, since we've been monitoring more frequently, what we've realized is that time, the lag time between water reaching the land surface, infiltrating, and reaching a water table can often be much more rapid.
And when much more rapid being days, much more rapid being hours, much more rapid.
It of course it will depend upon environments, and clearly, and it's an important thing for people to recognize, the diversity in soils is huge, and it will vary from place to place. But what maybe here we are in Bengaluru in the lateritic soils that you often see in areas of the tropics that are where you have soils that have developed on granites and gneisses, and those soil profiles have developed over millions of years. Actually, they're quite heterogeneous.
Right.
And what you can find is that in some of these environments where I've been working in East and West Africa, it is in the matter of hours to a few days to travel, so for instance, 10 or 20 meters down to a water table. Mm. And that is much faster than we ever, I would say, that most hydrologists considered in the past. Now, the downside of that is it means that groundwater is actually more vulnerable to pollution than we previously had assumed.
Right.
And so that...
And deep groundwater too is vulnerable.
That's right. Is vulnerable in a way, again, that we hadn't really anticipated. And the explanation for part of that is that the infiltrating water doesn't necessarily, you can use the word sample all of the available, what we call pore space, so the space between the grains of sand and clay, for instance, on the subsurface. It doesn't necessarily sample all of that. And it says, oh, there's a fast route. I'll go down that crack, or I'll go down that stone line, or I'll go down that preferential pathway, maybe form a root system. And it can go very, very quickly, penetrate very quickly. One of the other things I wanted to mention, and this is an important part. I want to just reverse for just a moment here. When we talked about more intensive rainfalls, fewer but more intensive rainfalls, one of the things that's sometimes lost, particularly within the climate community, is that the relationship between air's ability to hold moisture, and temperature is nonlinear. Mm. So that areas in the tropics, which have a higher temperature, mean annual temperature, compared to, say, mid-latitude areas where, I'm in London and Toronto and places where I'm from. And actually, because it actually follows an exponential, the further you are along in terms of the higher your temperature. So if you have a mean annual air temperature of 25 degrees and you experience 2 or 3 degrees of warming, we've already experienced more than 1, and we're on track for 2 very shortly. The intensification of the rainfall in the tropics is 2 to 3 times greater than it is at mid to high latitudes. So when we talk about 1.5 degrees and the Paris Agreement and
I know that sounds tiny.
That's right. It doesn't recognize the fact that the impacts are differentiated. And so, for instance, the more intensive floods, longer droughts, these are 2 to 3 times greater, that change is being experienced in the tropics relative to the mid or high latitudes. The importance, particularly, of groundwater in the tropics. As I said before, the intensification of rainfall, it will lead to greater runoff and flooding. But what we have observed from observation, many environments, not all, is that it also enhances or serves to enhance recharge.
Right.
And so areas in the tropics that are now suffering, okay, from this intensification of raw, the aspect of the water balance that is, if you want to call benefiting or increasing, is the groundwater. And what is affected is the soil moisture. So the farmers are experiencing greater risks associated with wilting and obviously soil moisture deficits associated with the growing of crops. And so what we're going to see really, if we kind of look towards the future, is if we want more climate resilient agriculture, yes, we can maybe look at seed varieties and changing cropping patterns. But I think at the heart of it, supplementary irrigation, in particular, but also perhaps, particularly if we're looking at substantially increasing food production, looking at irrigation or expanding the use of irrigation is something that's going to be fundamental, because the soil moisture is disadvantaged, if you will, by
because that
climate change.
extra rain is not staying around and soaking the soil in any way, but it's exposed to constantly kind of the heat and the sun, which is now increasing temperatures, and so it's going to dry more at the surface, which is where all of your root zones are.
And
Right.
therefore, where the fundamental need for that buffer, if you want to call it climate buffer, of groundwater to supplement the soil moisture loss to the atmosphere, it will be critical in the future.
Fantastic. I remember a few years ago, we did a participatory groundwater monitoring program in very, very deep wells, farmer wells. And we found exactly what you said, even 600, 800 feet bore wells, you would see a signal, within a month or two of the rain. It wasn't immediate, but these were very deep bore wells. And at that time, a lot of the old geologists would say, no, deep groundwater is like fossil groundwater and all of that, which subsequently a lot of work through of BGS and others showed that it's all modern groundwater. But you could see the signal even in very deep bore wells fairly quickly. But I wanted to take us down a little bit of a rabbit hole, literally, if you want, if you want to call it that, which is that these macropores that we're talking about, which is the preferential pathways by which what. One of the things that's always struck me is we hydrologists don't talk much to biologists, and we don't understand necessarily what the role of different variety types of vegetation is in creation of macropores. I know there's a lot of the ecohydrology work in terms of how plants take up moisture and so on. We went to the field together just recently, and we saw those big peepal trees in the field, and a lot of traditional older people in communities will tell you that the roots of the peepal tree are macropores because of the way they do it. And that's one of the reasons they had it in all of these crucial places. It's one of the reasons you have it. But when I look at actually the literature, if I had to ask you species-wise, which species enhance recharge, do we have answers to questions like this, especially when we're looking at native species like, or is there a lot of traditional wisdom that because we hydrologists are like physics and chemistry people, we kind of don't pay attention to biology and we're missing entire bits of the story?
I would say that's very true, meaning that we're missing parts of the stories because we don't have hydrologists, hydrogeologists, civil engineers, and others engaging with biologists, ecologists who are much more focused on the living material rather than the inert material, and that is a huge problem. I would say, for instance, now the mango trees. If you look, for instance, I spent a number of years in northern Uganda, and if you look in the dry season, you look and the grass is yellow and brown across the landscape, and it's beautiful, and it looks beautiful anyway. And then it's dotted with all of these evapotranspiring mango trees, which of course are in bloom essentially, as you see it.
At the peak of the summer when there's no, and mango trees are famously not irrigated, even in India.
That's right. And so the idea is what's, it's really simple. I use it for teaching sometimes just to show, okay, so the difference between these two is one is phreatophytic, so therefore it's taking water directly from a water table or it's accessing groundwater. And clearly the soil zone is depleted or is in a soil moisture deficit. And that's where you see the wilting of the grasses. And is another if you want to call it, worker in including infiltration, and it's termites.
Yeah, and earthworms and all of those other.
That's right. Actually, we specifically were sort of applying to work where they have observatories, where the ecologists are all focused on. Let's look at this area that in the kind of soil regeneration and the soil chemistry and biology of this area dominated by termites,
right,
and another area where there are no termites. And are you running any hydrological experiments? And they said no. And
no.
So actually it kind of works both ways. The ecologists
they
need
don't pay attention to the water. But in fact, traditional wisdom, again, they know that when there's termite hills, there's shallow groundwater. I mean, that's sometimes we unlearn things. And the third piece of it was when I was talking about the earthworms, one of the things, that a lot of, again, traditional, wisdom, old people will tell you is that when you have lower pesticide use, so you're not killing the entire soil microbiome, one of the important things that you have in fields is a lot of earthworm burrows because you haven't killed everything, because you haven't dunked it with a ton of pesticide. But earthworm burrows are preferential flow paths. And this is the part that's always kind of, really baffling. There's a reason why I'm asking you this set of questions, because your data shows that when it rains a lot, the rate of recharge is disproportionate. It's not what Richard's equation, which is water soaking through a uniform soil matrix, would predict, because the rainfall is finding these macropores or paths. Some of them may be physical, like granite fissures. Others might be things which are caused by tree roots, but also earthworms and literally rabbit holes. But on the other hand, when we look at mechanisms of how do you restore or increase recharge, we don't talk about those. In India, at least, 90% of the conversation is around managed aquifer recharge, right? You take the water to specific zones and then you allow it to percolate, which is important. Now, I know that when you've talked about focused recharge, you're talking about recharge in specific places. If you had a landscape which was full of rabbit holes and tree roots and that sort of thing, you would see rapid recharge in a whole bunch of different places, far more than you could get with a few check dams, right? And how does one think about recharge then when we kind of open up the world to say, wait a minute, recharge doesn't just happen through finding places where there's more granite or sand or whatever, more soil infiltration, but also finding places where there is. So you're not just looking at the physical properties of soil, you're looking at the biological properties as well.
I couldn't agree with you more. That one of the, even by its very definition, managed aquifer recharge, a lot of thought actually went into this, whether one agrees with this or not. Managed aquifer recharge, I said, needs to be intentional, meaning you planned to do this, okay? Well, I think the plans for managed aquifer recharge as it is currently practiced is very much dominated by, if you want to call it, civil engineering interventions. And I would definitely agree with the point that there has been much less attention to of biological solutions to how can we won't call engineer the landscape, how we can have a landscape that would allow or permit water to infiltrate more readily
through natural but biology or whatever. Ecology-led processes. It's important because in India, there's so much money that goes into managed aquifer recharge. I've been talking to you a lot about like water credits and all of this stuff. All of that goes into civil engineering structures. But civil engineering structures means that you've got to constantly maintain them. The beauty about nature is that nature maintains itself. And so if you had to literally think about the operations and maintenance of you trying to take water to a place which comes with silt and constantly desilt it. And I like to use the analogy of the myth of Sisyphus, the Greek mythology where Sisyphus was doomed to kind of having carrying the rock back up the hill. For me, in my head, managed aquifer recharge is like the myth of Sisyphus. Like you have all of this debris and silt and stuff that comes into these structures, and forever and ever and ever, you got to carry it back to the field. But if you were able to look at it in a more holistic way and understand some of the biological controls, then maybe you could escape the burden of the myth of Sisyphus.
I agree with that. And we talked earlier, just a few moments, about the lack of research and activity that's taking place between ecologists, biologists, and hydrologists. And I would say perhaps one of the problems with this is someone might say, that sounds like traditional knowledge, Veena. How do we know that?
Yeah, but let's invest and find out. It seems logical to me.
I would suggest that the time is right for much more research to be done on these matters. One thought I thought I would raise you a little bit of a story, perhaps from Bangladesh, and it's this idea of, is it managed or is it unmanaged in terms of aquifer recharge? And one of the things we found there is that widespread dry season irrigation for burro rice crop in across Bangladesh, and this is into West Bengal as well. This really kicked off in the 1980s and 1990s in particular, began to pump water down during the dry season. And one of the curious things that is that they would find that when the following monsoon, groundwater levels then rose. And actually, it's this business, we might get into this business of what you would call freshwater capture. And it was the whole idea that you wanted to expand the amount of irrigation and a dry season crop to improve food security. And I guess people hadn't really thought too much about what would be the sustainability or the renewability of this use of groundwater. And it's only through decades now of accumulated groundwater level data and our knowledge that comes from those that we recognize that actually this system where you pump during dry season, it lowers water tables during that dry season, and then during the subsequent monsoon, more water is able to infiltrate, but it's only able to infiltrate where the soils permit. But where the soils permit that infiltration, it is able to bounce back. Now, we're talking about farmers that are on hectare-sized plots, more or less. And what we computed is that over a 30-year period, that the amount of water that somewhere in the order of about 15 or 16 million smallholder farmers in Bangladesh had achieved was more than twice the reservoir capacity of the Three Gorges Dam.
I love that analogy of aquifers as dams we can't build.
Yeah. And it's this idea that you cannot build dams on the Bengal
large
Delta.
Flat places.
Large floodplains, you cannot build dams. So how do you achieve some degree of capture? How do you try, when the floods come, how do you keep more of those on the land? And
by creating space for the water underground is what you're saying.
Exactly. The other part about that, and I think there's E.F. Schumacher's bit about small is beautiful, and the whole idea that actually we don't necessarily need these large structures. We don't necessarily need to spend huge amounts of money, but we can often achieve things in a distributed manner if it replicated over a large area. And one of the curious things, getting back to that idea, is it managed aquifer recharge, or is it in a way unmanaged aquifer recharge? And it's this idea
or induced aquifer recharge in some
induced aquifer recharge. Is it the farmers individually did not know what they were seeking to achieve, but collectively they had achieved this. And I think one of the things that we're working with the Bangladesh Water Development Board at the moment is actually trying to be using the research, not just to explain what's happened. And of course, they're now the world's third largest producer of rice. Incredible transformation in a generation or so. But trying to understand from the research, actually there are some areas where depletion has taken place, and there are some areas where actually you might be able to increase that abstraction, but it's not having the knowledge to know where that works. And largely, it can be explained by the surface geology. So where the soils allow infiltration, you can perhaps possibly have sustainable or renewable increases in irrigation taking place, but there are actually a greater amount of area where it's not sustainable because the soils don't facilitate the infiltration. They're very clay rich, and you can have large areas where very little infiltration is taking place, and it's leading to depletion. So you can be smarter. Essentially, you can be smarter about what you're doing. Where it's renewable, do it. Where it's not renewable, maybe you should think about changing your crop type or certainly finding ways of reducing your pumpage.
If you find this episode to be valuable, please like the video and check out more episodes of the show. And don't forget to subscribe to the Well Labs YouTube channel. And if you think someone else, maybe a colleague, a student, a friend, or a fellow water enthusiast, might find this show useful, do share it with them. We hope to reach many more change makers like you. Fantastic, because you're making a very profound point, Richard, because I think what I'm hearing from you is, of course, start off with, you said a lot of groundwater recharge happens in through focused places, through mechanisms, not through water soaking through the soil, but through macropores and so on. And the large events have a disproportionately large contribution.
Yes.
And with climate change, you're going to see more and more of those large events. And most importantly, surface water infrastructure, which is what all water resources departments everywhere in the world are geared to kind of say, naturally is like, if you have larger events, build more dams. But instead, what you're saying is take that same money, invest it in much more water data, essentially. But that will really tell you how to manage it in a much more organic way, if you want to call it, where can you draw down and create space for rain, because you know there's going to be enhanced recharge, and where you have to put the brakes and allow the water to kind of recover. And that's actually a completely different way of managing water resources at large scales than is traditional wisdom. And actually, it costs very little to invest in water data, but even countries like India actually scaling back on monitoring and piezometric infrastructure. And I think what I'm hearing from you is that's a mistake. Don't do that. Instead, let's expand our understanding and monitoring and manage it a lot more adaptively.
I agree. I think there's an aspect here of think about the landscape in its, if you will, in its totality. So if we were to speak to a civil engineer and say, what is your biggest concern about flood risk? Actually, in many cases, it's not actually the volume necessarily of water. Flood mitigation and flood management is trying to reduce the peak level that takes place, because you want to reduce the amount of areas that are inundated and all that. And people think of engineering structure. So, for instance, I'm from Toronto, and in Toronto, they fell in love with concrete and cement, and particularly in the 50s and 60s and 70s. So they built all of these linear culverts throughout the city, and what all that did is greatly exacerbate the flood risk, because you're concentrating all of these flows into very linear channels. And of course, some of this was done because they wanted to maximize the amount of land that people could build homes on and things like that. And what are they doing now? What are they kind of woke up and realized? That's a really bad idea. Having meandering streams on rivers within a city, these are things that can expand and shrink and respond. They also absorb a lot of the sediment. And so you're actually distributing, if you will, the impact of flood events throughout the city rather than concentrating.
Right.
And if you kind of take that analogy a little bit and think about a landscape and a basin at a whole, if you've got heavy rains occurring and they're more intensive in the future, if you find ways that the water can infiltrate the landscape everywhere, then in the channel where it's coming down, you are reducing that load in the channel. And so I think it's having a kind of a much broader and holistic understanding of how the landscape can mitigate flood risk, at the same time improve the distribution, if you will, of groundwater in particular throughout that landscape.
I've heard you talk about China's Fund City efforts as well. It's important to keep saying that, because where land prices are very expensive in developing cities, there's a tendency to say, let's develop everything, let's concretize everything, and we'll somehow just build bigger drains in a few places and that's going to solve it. It's not going to solve it, because you can never build a drain large enough. You have to make the whole landscape absorb and not focus on individual points where you can actually somehow mitigate everything.
Yeah, I think that's almost being a bit more honest with ourselves actually we want to develop a particular plot. And I'm just looking for a rationale that allows me to do that. When you think about it, no, if you want to reverse that a little bit and think, no, we need to maintain these areas, and you need to accept the reality that a river and an urban river should meander. And yes, it's a little annoying because that means that there's less land to develop,
Right.
and that means municipal councils are going to get less tax revenue, less whatever, and that. But let's be honest about what we're doing here. We're trying to profit before people.
Right. Richard, I want to do justice to you because I know we've been chatting, about all of these mechanisms, but your profound understanding has come from very, very, very meticulous, detailed work on water data. And what I really like about your work, and you said it in the beginning that you're an empiricist at heart. And so what you've basically done is to look at the data and kind of say, what does the data tell me? And you've stitched together these massive, massive data sets across the world. Some of it primary, I know you do a lot of primary work in Africa, but some of it is then stitching together large amounts of secondary data as well. So can you tell us a little bit about your work on, firstly, primary work in both East and West Africa in terms of what did you measure and what kind of insights did that give you? And then some of those large data set work that you've done as well.
It actually goes back to the beginning of my career when I realized, and in those early days, I had the very good fortune of working with some excellent colleagues, and I'll name drop someone named Kalise Tindu Mugaya, who you know as well from Uganda, who's now the Commissioner for Water Resources Regulation. So he basically has controls the tap on the Nile moving northward from Uganda. And working with him in the early days, one of the things that dawned on both of us is, again, we talked earlier about the kind of dominance narratives in water management being surface water. And we recognize that we have lots of observations of rainfall, great. We had lots of observations of river discharge, something we can see, and that's easy. Almost nothing on the subsurface. There were no monitoring wells. Kaliste and I installed the first monitoring well in Uganda in 1992. And it's still now, of course, that record is giving us 3 decades of data. And we now understand from that and many other records subsequently how groundwater levels respond, if you will, to variations in rainfall, seasonal, and even daily events. And so I suppose one of the things that I have been pushing, not only to collect and maintain and curate is, I guess, one word, is data sets, particularly time series data sets, groundwater levels, but also just developing a better understanding of the subsurface from well logs and wherever you can piece together even information that we can get from river discharge in terms of base flow. So the real priority that I have been trying to do is groundwater is part of our water balance, our understanding of our hydrological systems, and it's been a kind of a lifelong and career-long effort to try and improve the amount of data, but also in the quality of the data sets that are being generated. There are some, and it has been not only a pitch to try and mine, if you will, historical observations of groundwater levels where they exist, but certainly to set up and establish observatories in many different parts of the area. And of course, this is something that is done with research institutions and governments within in country, and it's and then also find better methods of interrogating. What can we learn from the accumulated evidence? And I think that's been the most important thing. You sometimes, and I'm sure it's perhaps there's some evidence of it here in India, is that sometimes people can be gathering data, but data will remain, if you will, of limited use unless you are translating it into something meaningful and how it can inform how we operate and what we do in the landscape. So that's been a big key.
Absolutely. I think but the biggest travesties, in my opinion, is people looking at data only for model calibration and validation and not data for the insights it provides by itself. Yeah. But in fact, a lot of your deep understanding of focus recharge comes from just looking at the data and saying, hey, it doesn't follow Richard's equation. In fact, it's preferential pathways that are causing these rapid responses. And so I think the culture of data in water actually isn't there. At least in Indian hydrology, it's very, very low because most hydrologists in India are modelers. And I know both of us are modelers to some extent, but I also would prefer to be an empiricist rather than a modeler because I like to be data first. But I think some of those insights that you found in East Africa on focused recharge come from just looking at data, isn't it?
It has, and I would often ask people to be more curious. And one of the parts about this is whether one remembers when they first learned about hydrology. They're often really dominated by narratives that have come from textbooks that focused on examples, for instance, from New England or catchments within Britain, and I suppose not valuing the diversity of the environments that actually exist. And actually, some of my early work with Caliste and others in East Africa, we discovered, wait a minute, the way that we see this here in Uganda does not really look like the textbooks that I have been reading or have been, if you will, weaned on in terms of my understanding of hydrogeology. And that curiosity certainly really, I became fascinated. So one of the early bits there was we realized that the chemical composition of the groundwater didn't match that of the the average composition of the rainfall. And I'm actually speaking about something known as stable isotope ratios in oxygen and hydrogen. I won't necessarily go into all the details of that, but these are tracers. And what we found is essentially the chemistry of all rainfall collectively put together didn't match the chemistry of the groundwater. And there is something that happens in the tropics where the chemistry of that rainfall is often more dominated by the intensity of the rainfall rather than, say, the temperature of the rainfall, because the temperature remains fairly consistent over the year. And what we found was that the groundwater, the chemistry of the groundwater, much better matched the heavy rainfalls rather than the aggregated sum of all rainfalls. And that was one of the early indicators that, well, there seems there's a bias to the groundwater in its composition to those heavier rainfalls. And that was an example of a curiosity that was there. The other was Southern Ontario, people, where I'm from, near Toronto, people would talk about how long it would take for rains to infiltrate through glacial tills. Okay, and of course they would talk in the order of decades. Right, and here I am working with Caliste in the field, and we're seeing water arriving at a water table within days. And I would go back and speak to people back in Canada. There's a problem with your data, something really quite dismissive and patronizing, and then actually we stuck with it, and sure enough, it proved to be true. And another one, and maybe gets back to a little bit back to things here in Bangalore, perhaps, is with some of the early work. I was working in the United Kingdom, and what we found was that we were trying to understand there are rising groundwater levels in London and Birmingham. This is a very common kind of post-industrial cities in Western Europe. Groundwater levels are rising. If you are taking the underground in London, for instance, you have to appreciate that when you're on the tube, you should be underwater.
Right.
You're not underwater in the tube because pumps are actively pumping and dewatering the subsurface in London to ensure that you don't drown. And then the thought was, what could we do something with that water? So I was urban groundwater. How do you address the rising groundwater level problem? So we put in multi-level piezometers. So these are wells that can go to different depths. What we found, very curiously, was that the groundwater at depths of 40 or 50 meters into sandstone, into chalk, beneath London and Birmingham and places like that, what we found was that it was contaminated with fecal viruses and bacteria. Well, I presented this at 20 odd years ago at a number of conferences, and people just looked at me and said, "You're wrong. There is just no way that viable fecal microorganisms are migrating 50 meters into the subsurface. It doesn't happen." you're
They
wrong.
can't survive there.
They can't survive that. And actually, the critical evidence, and there's a curious thing, in the UK, we have something known as a fecal virus, no norovirus, and then there's something also known as Kasaki virus. Norovirus, very common in winter. Kasaki virus, much more common in summer. What we observed is that seasonality was reflected in the viruses that were assayed in the...
So it wasn't even months delay. It was much lesser than months.
It was less than that. Now, today, people will say yes. And it's not as if their survival is much enhanced. We just recognize now that particles, microbial particles, can move through the subsurface much more more quickly than we previously thought. And it's this idea of sometimes challenging paradigms with observations, because otherwise people won't accept that. And another, maybe to get back to some of our earlier conversation, in understanding how water infiltrates a landscape, you will often have people with, and maybe you did this as well, during your times in engineering, we call them permeameters. People will take a clump of soil, put it together, and see how quickly water can move through this sample of soil that I have dug up with a shovel and put into a cylinder to see how fast water moves through it. Well, to suggest that that cylinder that you're pushing water through is representative of soils more generally, I mean, we can almost laugh at that right now. That was the standard way of investigating. We call them infiltrometers, of how water can move or the measure. Modelers often state, well, the infiltration capacity of the soils are this. And I said, well, how did you come up with that value? Oh, well, it's, a table of values I found from a paper where someone did this in a laboratory somewhere. Well, and then you're now imposing that on
the entire landscape.
Entire country.
Yeah.
So I found, for instance, that I would have modelers challenging me. No, water cannot move that quickly through. And actually, what I have now found is the modeling community is catching up with, if you want to call it, those focused on observations. And more recently, the idea of bypass flow is now, if you will, infiltrated the modeling environment. And you will now see it's fairly common now to see modelers incorporating macropore flow, but they call it something maybe like bypass flow in terms of their models. But what's helpful about that with the modeling community, if you will, adapting, is we're now coming up with models that, albeit it's challenging to represent these things, but at least acknowledge that these processes are happening.
What I've understood from everything that you've said is that, of course, we are seeing a lot of rapid response in deep groundwater. But does that mean that all deeper groundwater is modern? I know that's the case in India, but what does the data show?
What the data shows in many environments, and I wouldn't be surprised if it was also here, also in Bengaluru, is that we think of groundwater in the subsurface and this tremendous buffer that allows us to weather, for instance, years of low rainfall versus, and particularly even maybe multi-year droughts or periods of low rainfall, is that groundwater isn't all derived from last year's rainfall or even the last 2 years of rainfall, although those can make clearly a difference on water levels. But when you are pumping, for instance, water at depths of, I work in meters, so if you excuse me here, so 300, 400, 500 meters. One of the things that's come out of research over the last decade or so, and this uses tracers of residence, what we call residence time, is that we often find that the groundwater itself is a blend of sources, and some of these could be very old waters versus some of them newer. So when you are, for instance, drawing water from 400 meters down, and you take a cup of that water, within that cup, there will be water that probably is in the order of centuries, if not even millennia in age, as well as water that is derived from possibly last year or in the last few years rainfall. And so it is a blend. And in a sense, it's almost, I won't say it's deliberately a blend, but it is just by the processes by which groundwater systems are replenished, is that it does not all result from, otherwise this is a bathtub.
Right.
Okay, and it's aquifers are not
Not
bathtubs.
bathtubs, which is why we need more data on aquifers because they
That's
are
right.
not homogeneous.
But it also, here's the other point, recognizing the vulnerability of groundwater too. So when we identify groundwater as being, say, centuries in age, and for instance, we can all then say, oh, wonderful. There's no risk of any kind of pollution because it's taken so long to get there. Actually, that is a false assumption because although you have one indicator that might tell you it's centuries in age, it very likely, and particularly, another way to think about this is if you have groundwater levels that are very deep, and then for instance, I've even heard while I've been here, well, the last couple of years have been quite wet. And we've seen a strong response in the groundwater levels at 500 meters.
Yeah.
Well, that tells you something, okay? If the groundwater at 500 meters was not accessing the replenishment in part from then the water levels wouldn't be responding.
Right.
So the water level responses, that those deep groundwater level responses are telling us actually we are seeing water moving very quickly down. It doesn't mean all of that water is from the last few years, but it means contributions are. So it just heightens to all of us and make us all aware groundwater is, and this comes from all the empirical data as well, groundwater is more vulnerable to contamination for a long time than we previously thought. But also recognizing that that glass of water that you take from that deep well has a whole range of ages, if you want to call it, or has spent some of it relatively recent and fast moving through, and some of it maybe longer and slower. And so it can have a very wide range in what we might call residence time in the subsurface. Something sobering for us to recognize when we understand how we use groundwater.
Yeah, indeed. Do you have our episodes running in the background? If you're curious about a technical term that we use or an acronym we've forgotten to expand, check out our video episodes on YouTube. We have on-screen explanations that might be useful. Let's go a little bit to the large data sets where you kind of looked at, was it 170,000 well records, which kind of allowed you to pinpoint sources of depletion and places where groundwater levels were actually rising. How did that work come around? Because the work that you've just talked about so far is primary work, and this is now sort of synthesis of large-scale secondary work as well.
Yes, so that this is work that was done with some colleagues at University of California, Santa Barbara. So I'll just name drop Scott Jaseko and Deb Peroni, and who led this work. And they worked with myself and a colleague at University College London named Mohammed Shamsadua. And collectively, we're putting these data sets together. I refer to them as Shams. So Shams and I were putting together data sets coming from, for instance, tropical Africa, South Asia, and some other areas in Southeast Asia where we had connections, colleagues, and long-term working life. And Scott and Deb had been looking in other North America, but also they're master data compilers, both of them, and they're lovely to work with. So the ultimate data set was about around 170,000 wells around the planet, and these take a great deal of time. It took us about 3 to 4 years to, if you want to call, unpick if you want to call it the messages or the signals coming from these data. And one of the things that came out from that really was that, unfortunately, we are looking at groundwater depletion that is essentially global in its scale. I should preface this by saying it was just over 40 countries where we had 178,000 well records. So it wasn't truly global in its sense, but it was the largest data set that's been put together so far. And one of the key things we found is that not only is groundwater depletion a problem in many of those areas, but actually in quite a few areas, the rate of depletion is actually increasing, intensifying. The main, if you would, a kind of summary that came out from that is that the areas where groundwater depletion is most acute are actually in dryland environments. Mm-hmm. And that wouldn't necessarily be all that surprising, but it's also dryland environments which are agriculturally intensive.
Right.
And again, that might that again might stand to reason, but it was very kind of helpful in that previously we've been relying on sometimes some satellite data. There's a data set called GRACE that people have often used. But there's quite a few uncertainties associated with that work, and it operates on very large scales, about 100,000 square kilometers, which isn't really giving you the granularity you might want to really understand and unpick what's going on the ground. But one of the things that also evolved from that work was that we very curiously found there are areas on the planet where, in drylands, agriculturally intensive, the groundwater levels are actually recovering. And we're seeing rising groundwater levels, obviously from a bit of a deficit, but we're seeing, if you will, rising groundwater levels rather than declining groundwater levels. And that, for us, rather than having a doom and gloom perspective on this, we kind of saw that as inspiration. If there are areas that are agriculturally intensive, and drylands where the water demand or the freshwater demand to grow food or also to provide public water supply is high, why is it that the groundwater levels are recovering and responding? And we found that there are a range of, if you want to call it, instruments or explanations as to why this occurs.
So one of these regions is the Sahel, right? What you call the Sahel paradox.
Yes.
Okay. I'm just trying to explain where people might be looking for those places.
Yes. So, yes, one example is is in the Sahel, and what's happened there is, I would say, in the Sahel, the use of groundwater hadn't been necessarily all that intensive, as an example. But where the groundwater, one of the reasons why that's rising is this. Again, a little bit like the green revolution that took place within Asia, that you had an agricultural intensification that took place. Didn't involve necessarily large amounts of water, but what it did is it cleared a grasslands. And these are the grasslands within the Sahel are often deep rooted, and there are reasons they need to be deep rooted. Otherwise, how they're going to survive, often through the dry season. But what happened was, the expansion of agricultural production led to the clearing of this grassland cover and the replacement with shallow root crops. And what that meant was, and again, when you can imagine when you're putting the saplings in the ground, that they have their ability to evapotranspire, use water, is much less than the former vegetation or natural vegetation of the grassland. And so what that meant was that with less evapotranspiration, you there had more water on the ground. We sometimes refer to it as blue water, so the runoff or the infiltrating water. And so what they found is, during the Sahelian drought, river discharge was increasing
because of base flow
and base flow and runoff, and also groundwater levels were rising.
That's insane, really. But this is why I don't get it, because it's a hot, dry place. You're in the middle of a drought, and drought meaning agricultural drought as well. And yet you're sitting on this massive gold mine, but not tapping into it. Why is that?
It's a good question. I would say, in part, people have, for very long periods of time, relied on what they have at the surface, what they can see, and what they can access at relatively shallow depths. And when I say access, the capacity to install wells within this environment. So the tube well revolution that has happened in South Asia and other locations, you haven't seen that, if you want to call it tube well revolution, take place. In part, there are a range of reasons in terms of the cost, which has often been a major factor in influencing how groundwater has been exploited. And so, maybe just to finish that point on the Sahelian paradox, so the rising groundwater levels are even causing a problem in places like Niamey and Niger. People are certainly looking at ways of developing groundwater. So there are, and so they, at the moment, they're not offsetting those rising groundwater levels with groundwater abstraction, but there are plans in place, and this is much improving, if you will, and call it the food security and the resilience of food production. use of groundwater for irrigated agriculture is very much on the agenda. And actually, part of our work under the Clarity research that we're involved in is seeking to better understand what the capacity will be to deliver water for irrigated agriculture.
This made me really think about over the last few days, we've been traveling around the Bangalore landscape. And one of the things we've heard from people around India, of course, is in the opposite end of the spectrum. We've overexploited, shallow aquifers have long disappeared. And one of the refrains we heard from a lot of local activists or environmentalists was this idea of visibilizing rather than invisibilizing. So this is a very interesting set of kind of comparisons because in a sense, people have talked about groundwater as Africa's invisible resource, right? But then saying, how do we visibilize? What we've learned from the Indian context, don't make it visible via tube wells because people then don't understand what the levels are. But if you do it via open wells or dug wells, so historically, there's been a long culture of, we saw the step wells, which are these beautiful architectural structures to tap shallow groundwater, but also open wells, which can be up to 30 meters even deep. You'll see them throughout South India. It's curious to me that open well culture never developed in the Sahel, and maybe because their groundwater levels were deeper than that historically. Why was it that an open well culture never developed in some places? Was it just coincidence, not enough population density? They were primarily pastoralist. What was the reason?
It's a question I'm probably not able to answer, certainly not definitively. What I would say is open well culture of the nature that you're speaking out exists. In fact, that is often the traditional, they call them cemented wells, and there is often is often the village well, if is there, and that is, with access by the community. I think it's in essence, it's the magnitude of the yields, perhaps, that has been constraining in terms of using it for much greater people using much more water. The water use, individual or per capita water use from these things is relatively small.
But how can it possibly be higher in a tube well? Because in an open well, if the yields are low, the open well acts as a storage as well.
It's the pumping technology. So are you manually removing the water from that open well, or are you pumping water from that well, say with electrical submersible pump? This often explains kind of the difference. I'd like to your point about this idea: is it visible or invisible? And I think one of the issues with the deeper groundwater is it just seems some sort of
magic thing,
gift from God or something like this that allows this to take place. And so people just. It's almost like gold that's coming up from somewhere, and then almost we don't have any responsibility to it.
Right.
We don't need to care about it or preserve it or think. We just take the bounty as it comes.
And then one day it's gone, right? You heard one of the activists say the well was alive and then one day it died, but we don't know what happened. We never saw it get sicker. While with an open well, you actually see that.
Exactly.
And so then it induces a way to conserve. So it's curious to me how some of these conversations that we are having in India translate to the African context.
Yeah, I think one of the curiosities is we have an example in Tanzania and in Dodoma, which is the capital of Tanzania, where they have people sometimes refer to them as basement aquifer. So it's out of weathered and decomposed granite and gneiss, and they are pumping huge amounts of water from this system to supply Dodoma with a water supply. And there are big concerns around depletion. They are the wells there are sort of 80 to 120 meters deep, and water levels are down around 25 or 30 meters. And people are wondering, okay, these water levels could go down even further. And there is been a lot of discussions in these basement aquifers within tropical Africa about what about deeper water? Is there perhaps a deeper system we can exploit? And I think what's been really helpful and inspiring, really, particularly from our colleagues from Tanzania who are here to see this in Bengaluru, is maybe it's a fallacy to believe that the deep groundwater is going to be some magic solution that's going to allow them some sustained water supply over a period of time. And one of the things we've been doing within the Clarity Project is try to come up with some water budget calculations so we better understand how this system works. And I think at what we can now, under Clarity, advise the Ministry of Water and the operating company known as Duwasa, who is providing the water supply within Dodoma, is you're pretty much at the limit of the renewability of your shallow system, if you want to define it in those ways. And actually, anything further here, you're beginning the race to the bottom. And in such that you're not going to capture. The freshwater capture will be exceeded, and exceeding that freshwater capture created by the pumping wells themselves. All you're really doing is just drawing from an increasingly limited amount of storage, which is in the deeper rocks to the depths of 500 meters that you're familiar with here. And so what Bengaluru, Chintamani, and other these sort of examples can do, they can say, look, you don't need to go down this pathway. Manage with what you have at the surface. And whether that means, importantly, thinking about ways of whether it's managed aquifer recharge or even other structures to help induce further water infiltration into the subsurface. But it's also, and this is really interesting, we've got, particularly from the example in Chintamani, you've got to get your house in order. You've got to make sure that your how you are dealing with your sewage, your fecal waste that's coming from each of the residents on your within the landscape, and how you deal with the solid waste. Your water supply is around you. What's recharging the wells that you are using is in front of you, and you don't want to be sending poor quality water down there because it's not a viable, sustainable, renewable long-term solution.
Right. In India, almost everybody is downstream of somebody. And so all of our water is getting contaminated by somebody else's sewage and solid waste. And unless we fix that, there's no magic water. There's only so much rain. It falls in the land. It goes into the ground. It goes into surface water bodies. That's it. There's there's no mythical, pot of gold at the end of any rainbow. Can we? I mean, what something that you just said about this idea of renewability of groundwater? This is a crucial kind of concept that comes up over and over again. I did want to kind of have you unpack it, but also kind of contrast it with how you think about renewability of groundwater in light of some of the work that, for example, Brederhoft and others have done on what they call the groundwater budget myth. Have you seen some of that? Which basically says that ground and surface water are integrated. You can't look at groundwater separately. But what you can do is to understand that when you're talking about renewable groundwater, it still comes at the sacrifice of base flow or something else, because if you're drawing down, but that's okay. We make choices, in a sense, about how we define the bounds of renewability. So talk to me about how you think about renewable groundwater in that larger context.
Sure. In doing so, I'll try to address this question about the water budget myth. So when you pump a well, the water level instantly, if you will, in a well goes down. And what that means is that the water level outside of the well and adjacent to the well is higher than the water level in the well. And as that water level in the well goes down, it induces flow. Gravity is forcing water outside of the well into the well. So we call them in hydrogeology cones of depression. So this is where the drainage, the well itself and where the intake is in the well becomes a drain. It is draining water from the surrounding geology. And there's a concept in hydrogeology known as freshwater capture. So what's actually happening, if you think about it, is the well itself is beginning to capture water from the surrounding geology. As it does that, water that might have gone somewhere else, base flow to a river,
or to an ocean,
or
in the case of Bangladesh,
or to an ocean, but also to the roots of a mango tree, is now going to the well. And so freshwater capture, if you will, the water that is captured. So a well will keep pumping and the water level will keep going down until the flow coming into the well matches the flow going out of the well.
Right.
At that stage, you enter what we might call, some people call pseudo steady state, a kind of scenario where what's coming into the well equals what's leaving the well, and then the water level becomes essentially fairly stable. We sometimes call dynamically stable. Therefore, pumpage equals capture, and that's the kind of like a study. But what is happening and how we define and compute freshwater capture? It is the changes in recharge, okay, plus the changes in discharge. And when we think of changes in discharge, it means you're denying water now either to a river, to a spring, to a mango tree, okay, to the ocean. You're now denying that water. That less water is going there, and more water is coming from recharge entering the well. Why this relates to the water budget myth and what they were saying, and there's clearly a truth, is the recharge now, a pumping well, the recharge now entering a pumping well is different, it's greater than the recharge that was occurring before the well was pumped.
Right.
And that's why they said the water budget myth, because people have often computed recharge under what we might call passive, non-pumping conditions and said, that's the renewable groundwater resources of this region is based on the amount of water recharge under passive conditions. And Bredhoff and others said, that's a nonsense. As soon as you pump, you're changing the system.
But Bredhoff and others also said, look, recharge is not a magical. It's not in India. We have this myth called this mythical story called the Akshay Patra, which is a thing which is a bottomless kind of thing where it's not going into a bottomless pit. It's essentially going to the aquifer and then discharging as base flow in equilibrium, non-development conditions. So in a sense, you can capture it, but you're going to lose base flow in the process of doing it.
So, for instance, I gave you the example of the Bengal water machine previously. One of the consequences of that is when people are pumping water down during the dry season in Bangladesh for burro rice irrigation, they're actually denying, explicitly denying flow, base flow to the rivers. So what you're seeing certainly in areas where pumpage is, some depletion is taking place, you are seeing base flow to rivers and rivers drying up during the dry season. So there is in life this expression, you don't get something for nothing, okay? Right. So it is a societal question, in truth. Do I prioritize the water for irrigated agriculture over the water for base flow to a stream or river?
It's a little, you're basically saying we are okay with saying we will sacrifice some base flows in the dry season in order to supply irrigated agriculture, but create space to capture flood water in the wet season. So in some sense, you're also increasing base flow because you're actually capturing a lot more water than you would have captured otherwise.
Yes. And so I guess that what it also means is this is why monitoring is really quite important, because you can say, oh, wait a minute, it looks like we want some water, let's say for irrigated agriculture, but actually what we can see now is the rates that we're pumping at are now having an impact beyond which we had anticipated or we as a society, community feel is desirable. So we now need to reduce the amount of water that we are using for that. You asked me earlier about all the data kind of globally and everything. And what I didn't give you is some of the examples beyond, we talked about the Sahel, but where reductions in demand have allowed for groundwater levels to recover. And this is sometimes these have been economic instruments where you actually make people pay for the amount of water the amount of groundwater that they are abstracting. And one example was a famous kind of example is in Bangkok, where they were suffering from groundwater depletion there for several decades, and actually addressed it all by simply changing the levy and increasing the levy on the use of groundwater. There are other examples, and one went from the Barind in western Bangladesh. These are just examples I know. So, where people have switched from burro rice irrigation now to wheat, and and which is using uh, between a third, around, well, certainly 40% of about the what you would use for to grow rice. And I think it's recognizing that there are some strategies we can use. Some of them also involve supply side ones where there are efficiencies perhaps in managed aquifer recharge, where you're actually getting more water going into the subsurface to sustain that abstraction. But yes, so the idea is trying to find kind of solutions where you are keeping, if you want to call it, this imbalance, where you don't have the amount of you that you pump exceeding the capture that is possible. And that's the way that you can try to keep, if you want to call it, or where groundwater use becomes renewable. Okay. And I say renewable, I would say in a particular context. Renewability here, we're really talking about the physical system itself. What can the system sustain? And it may be that a certain amount of, it's getting back to your point, a certain amount of abstraction may be physically sustainable, but undesirable, meaning it reduces base flow. It
Well, it may
reduces
be that it's
springs.
physically sustainable with impacts that we are willing to tolerate.
In the first instance, we would say it's renewable. And then we might say it's sustainable because the impacts are those that we are willing to accept.
Right.
And it leads to access for the many, or if you will, that is as equitable as we can currently manage. And we would therefore say, for us as a community, as a society, we consider this to be sustainable. But in essence, that's a community stakeholder decision, not an engineer's decision.
Richard, we've been talking a long time, but I wanted to make sure that we end with getting a few of your thoughts on, if you had to look at kind of, if you're a young person starting your career today in the space of groundwater and empirical groundwater work, if you want to call it, what would you be looking at to do? What's exciting in the field for you?
Getting back to what we've just been discussing, I feel to me that the renewability, if you will, the renewable use of groundwater as a buffer in the coming generations, as a strategic, distributed buffer that allows people access to water during drought, during dry seasons, is so fundamental, and that absolutely essential that this that we find ways, pathways to this renewable, sustainable societal decision response. And one of the ways I wonder is, in our world, so much seems to be revolve around money. And so if I was early in my career now, I guess what I would say in my discovery, in my career, it was there were so few data to understand the groundwater system that for me it was to better understand how this groundwater system, and that seemed like the opportunity at my. Now that we're getting there, and there's a lot more data. Still, we'd like to have more, but there's a lot more data on groundwater. For me, where I see a real growth area is how can we value the valuing of groundwater. And just imagine for a moment if there was no groundwater. How would communities in remote areas, well off any kind of articulated grid, how would they have a water supply? How much do their lives rely on the availability of that groundwater? And if we think of dryland cities, they have to find ways of using their water resources and the water and that buffer beneath them strategically, but somehow we don't value it. And when I say value, I mean now I'm speaking really and getting into economics. Are there ways that we can begin to either put a value? It seems in environmental management that some of the best ways to communicate to policymakers is: are you aware of the cost that decision you've made has consequences for groundwater? And what are the costs really of that for groundwater? And what are the replacement costs if that groundwater is no longer there?
Or it's fully contaminated.
Or it's fully contaminated. What are now the costs that you will have to bear as a society, as a community? And think about that carefully. The natural environment is giving you something incredible, okay? But you don't value it because you seemingly don't put any kind of it doesn't figure in your financial calculations. So I wonder, and this is just that whether, as a career right now, getting into the economics of groundwater and understanding and finding ways of valuing it. Clearly, I think the most persuasive person in taking this would also have a solid grounding and understanding of groundwater in its role in the community, but also groundwater and the science of groundwater. But if they could marry that with an economic understanding and
an ecological understanding, both.
yes, and in a kind of environment, and we could think of it from kind of environmental economics to environmental ethics. Someone kind of combining that, I think they may become our long sought after advocate, if you will, for groundwater in the future, and that would be super.
Fantastic. Richard, it's been an absolute pleasure chatting with you. We went down a few rabbit holes, but I think we covered most of your career. I just wanted to say there were aspects of Richard's work that we didn't get a chance to cover because we also spoke to Alan McDonald, and you and Alan have co-published so much that it was a little bit of a dance to say, okay, what am I going to talk to about with Alan and what am I going to talk to with Richard, so we can really kind of cover a much wider range. But of course, you've been equally involved with a lot of the isotopic work we've spoken about with Alan, as well as the Ganges water machine and a whole bunch of other things. But just an extremely rich career that we've only kind of put a very, very small spotlight on. So thank you so much for making time and chatting with us. It's been an honor and a pleasure.
Okay, great. Thank you. I've really enjoyed this. Thank you. Thank you for having me.
That's it for this episode of the Water Data Podcast. Thank you for listening till the end. If you enjoyed this conversation, please subscribe to the Well Labs YouTube channel and share this episode with your friends and colleagues. You can find the Water Data Podcast on all major podcast platforms. Until then, stay curious and stay connected. Thank you.